Hi everyone, it's Mama J. Hope you guys had a great weekend. Today I want to talk about what's going to be on our test. I want to discuss some concepts that I feel that you should understand. The first concept I want to go over, we actually did not go over in class. So I do want to review it briefly so that it's a review from you. It'll be familiar from the previous examples that we did for the last test. But if you have two substances, let's say water or milk or something, and you're mixing, let's say, a hotter temperature of water with a colder temperature of water, or you made some hot milk but the milk was too hot, so you add some cold milk to it, for example, as long as it is the exact same substance, you can actually determine what the final temperature is based on the mass, as well as based on the initial temperatures of the substance. So for example, let's say you have a sample of water that is, let's say, 50 degrees, and a sample of water that is 30 degrees. Okay, and this sample has a mass of, let's say, 70 grams, and this sample has a mass of 35 grams. Okay, so the mass ratio here is then 2 to 1, because this is twice as large as this. Okay? So if the mass ratio is 2 to 1, what we can actually do is add the mass ratio, and it will give us the total energy parts, the total parts of the substance that are contributing to the final temperature. So 2 plus 1 equals 3 equal parts. And what this tells us is there are 3 equal parts of 70 and 35 of 35 grams that are going to contribute to the final temperature. So the temperature ratio then is 1 to 2. Why is it 1 to 2? Well, since this has twice as much mass, it is going to change half as much as this one, which, since it has half as much mass, is going to change twice as much. So the temperature ratio is the reciprocal of the mass ratio. So now, once you know this, what you do is you take the temperature range. So if you have the temperature range, okay, and that is from 50 degrees to 30 degrees. So it is a 20 degree range. Okay? If you take 20 degrees and you divide it by 3, let me go ahead and get my calculator. It'll give you 6 point something. So 20 divided by 3 will give you 6.6666667. Now, I'm going to put a long series of decimals here. And the reason for that is if you round too early, you're going to get a different answer. So it is 6.666667, let's say. Okay? You'll see why when I get to the later part. So now, if you look at the change in temperature, okay, remember delta means change. The delta symbol means change. The change in temperature is the amount that each 35 gram mass is going to contribute times the temperature ratio. So 6.666667 times 2, or times 1. So 6.6666, how many did I put there? 1, 2, 3, 4, 5. 7 times 1 is equal to 6.6667. Okay? Okay? And 6.66667 divided by, times 2 is equal to 13 is equal to 13.333334. So now what we do here, okay, let me go ahead and move this because it's probably going to be in the way. So what we're going to do here is we're going to take this number and we're going to either add or subtract it from the initial temperature of the water. So in this case, this water is 50 degrees. It's warmer than 30 degrees. So if we mix it with the 30-degree water, the water temperature is going to cool down. So I'm going to subtract 50 minus 6.66667. Okay? So 50 minus 6.66667 equals 43.3333. Okay? So this is the final temperature. Now, since you're mixing a cooler water with a warmer water, the temperature is going to go up. So 30 plus 13.333334 is going to give you 43.3333. Oh, that does not look like a 3. 4. Now, obviously, we don't have a thermometer that is this specific. So we would go with, let's say, 43.33. And as you can tell, these numbers are the same, okay? Because the further back you go into decimals, the more precise the measurement. But you cannot have a measurement that is more precise than your least precise instrument. We do not have a thermometer that can go back this many places. This is why I encourage you to keep the decimal places long. If you would have rounded it too early, you could have had something like 3.3 and 3.4 over here. Okay, which a student would say, well, that's wrong. But when you're looking at this, the accepted calculation with an error is 0.01. We are well past 0.01. So this is technically considered the same. So as you can see, since these numbers are the same, what that tells us is that we got the correct answer, because since this is the final temperature and you're mixing them, the cold water and the warm water ultimately are going to be the same temperature. Since they are mixed, they must reach the same temperature. So you can identify based on what their masses and their beginning temperatures are, what the final temperature would be. This is important for you to understand how to do. Okay. Understanding the difference between an insulator and a conductor. For example, if we're holding a pot. So this pot here is sitting on a heat implement. Okay, let's say it's a flame. Okay. Since this pot is sitting on a heat implement, as we often know, any of us who've ever spent any time in the kitchen, yes, although the base of the pot is getting hot, you also do have the handles, particularly on one of those pots that has smaller handles. The smaller handles, because they're relatively close to the pot and they tend to be directly above the heat implement, or at least part of it, what you will see is those handles will get hot. Also, you do have some older pots with longer handles where the pot is the same material as the handle. It's all metal, so you have to use something to be able to pick that pot up. So in this particular case where the handles are shorter, they're closer to the body of the pot, or in a case where you have an all metal pot that doesn't have a Teflon or other type of material on the handle, you would use something like a towel or an oven mitt or a pot handle, something to hold, a pot holder or something to hold the pot so that you don't get burnt. That functions as an insulator. An insulator has two jobs. Number one, it keeps something the same temperature, and number two, in this particular case, it prevents thermal energy from being transmitted from point A to point B. So the insulator, in the case of a pot holder or an oven mitt or a towel, it actually prevents the thermal energy from being transmitted to your hands and from you burning yourself. So understanding when an insulator would be used and when a conductor would be used would be important. For example, if you're trying to create a solar oven to heat food, a solar oven obviously would be made out of a metal, or you would attract sunlight to it or something using a conductor because you want that thermal energy to enter into the system. Okay, it's a lot of reasons. It's one of the reasons why maybe over a campfire we'll actually build or wrap food in aluminum foil, because it allows the energy to be conducted into the foil, trapped within the foil, and it helps cook the food better. Okay, so one of the other things I wanted to go over, we spoke about thermal expansion briefly in class today, but thermal expansion is extremely important to understand, because the thermal expansion is actually what causes, let's say, a floor to buckle if it wasn't installed properly, or a door not to close correctly within its frame because of the expansion of the door. So to explain what thermal expansion is, when a substance has thermal energy that enters its system, it's hot outside, your air conditioner stopped working, and your floor, for example, is experiencing temperatures that are not characteristic of what it's accustomed to, the particles in the floor are going to begin to vibrate and they're going to begin to expand. Okay, so your floor will begin to expand. So if the floor was installed improperly, let's say it was installed exactly from wall to wall and there was no room for shifting or movement, what you'll have is a situation where the floor will begin to buckle, because as there's expansion, there's no room for expansion. Once it goes out and there's nowhere else to go, it will start to buckle inward. Some of you may have experienced the door where sometimes it fits in the door frame and sometimes when thermal energy is involved, it's hot outside, for example, or the AC is not working, you go to close the door, and instead of being able to just let the door go and let the door close on its own, you actually have to provide a little bit of assistance to the door. You have to push it. In some cases, if the door was not properly fitted in the door jamb or the frame, thermal expansion of the particles in the door will cause the door to swell, and because there was no given within the door, it will actually stick. So you actually have to put some force behind trying to close the door. Okay, so you'll have the door actually get stuck, or it won't close on its own, and you actually do have to put some force. Okay, so when you are putting up a door or you're putting in a floor, you have to leave a little bit of forgiveness for temperature changes, because as something heats, thermal energy will enter into the particles and cause them to move faster and cause them to expand. That is called thermal expansion. Something very important to note, thermal expansion does not have to do with the loss of thermal energy. So if something cooling down is not experiencing it, they're two totally different things. I'm addressing this because I noticed that on the bell work, some people misread the question. I want to make sure that on the bell work you understand thermal expansion has to do with thermal energy entering a system and causing the particles to vibrate and spread apart. Okay? We talked about the function of a double boiler because many students had no idea what a double boiler was. So a double boiler basically is two pots, one pot that sits within another pot. And the purpose of a double boiler, for those of you who don't know, is to heat a substance that you want to control the temperature it is exposed to. See, when you place a pot on a burner, it is very difficult to control the temperature of the burner and therefore difficult to control the bottom of the pot. As a result, you can't control the temperature that whatever is in the pot is exposed to. When you put water in a pot, the highest temperature water will reach, despite what the temperature of the pot is, the highest temperature the water will reach is 100 degrees Celsius. And the reason for that is because 100 degrees is the boiling point of water. And since it's the boiling point, water undergoes a phase change from a liquid to a gas. Until it completely converts to a gas, it's not going to climb in temperature anymore. So this is effective for a double boiler because it forces the pot that's on top to stay at a maximum temperature of 100 degrees. You can control the temperature of the pot and therefore the temperature of the contents of the pot much better. It's great for making fondues, melted cheeses, melted chocolate. Many bakers use it as a way to be able to heat and melt certain substances without burning or scorching them. They're also used when you're heating things like beeswax or any type of coconut or shea butters. They're used in the process of making lip balms and lipsticks. This is a very effective process because it prevents the materials from reaching a temperature that is too high, and as a result could damage or denature the cosmetics. So that's what a double boiler is. But the reason we were talking about a double boiler is because the understanding of the double boiler, conduction is the process by which thermal energy enters into the double, from the heating implement to the pot, and from the pot to the water. Now the water becomes evenly heated because it is a convection current. Okay, as the water is heated, the different densities cause the cooler water to sink and the warmer water to rise. And as you have that motion that is constant throughout, as water is being heated and the water at top becomes cooler than the water below, you have that mixing of water through that convection current. Okay, conduction from the water to the pot and conduction from the pot to the substance within. And if it is a liquid, then obviously a convection current would follow as well. So basically these pots function by convection and conduction. Okay, so it's important to understand that. And those were some main points that I wanted to cover. Understanding energy transformations is very important. And understanding the differences between renewable and non-renewable energies. Know what energies are renewable and non-renewable. Non-renewable meaning fossil fuels. Renewable meaning the solar, hydro, electric, geothermal, tidal, wind, all of those are renewable. Coal is a non-renewable. So understand, we've listed all of them in our book. Understand which ones are renewable resources, which one is a non-renewable resource, and different methods that we've used throughout our studies to determine what the best course of action is to use. Also, we did have the ice labs that we did. We did 3 ice labs. The first one was an ice melting challenge. The second one was an ice preserving challenge where you built the insulators. And the third one was melting ice in warm water and determining the the caloric transfer from the warm water to the ice cube to make it melt. Please make sure you understand all 3 of those labs. Those are very important. So in terms of what we've done, in addition to the previous video that I posted, that's pretty much everything I have that would help you for tomorrow's test. If you have any questions, please feel free to reach out. Hopefully this was of help, and I look forward to seeing you tomorrow. Have a great night.